Welcome to Efiwe, excellence without stress.
Hello guys, this is Efiwe, excellence without stress. And as you know, I remain your most favorite chemistry teacher, Godson. Today I'm going to be taking us through a journey. And on that journey, we are going to be learning some really interesting things. Let's talk about something first. How exactly do you think we perceive that sweet egusi soup Mama Kule was cooking that day? She was in her own house, but from my own house, as she was cooking the soup, I was chopping the soup with my nose. Abi, the smell of Dr. Chike's perfume when he passes me. Or haven't you noticed that the freshener, the air freshener in front of your mommy's car, that you can actually perceive it from the back of the car? Not just the back, even inside the boot sometimes, it smells. To answer this question, let's talk gases, because the reason all these things happen is simply because of the existence of gases. Without gases, automatically these things will not be happening. Understanding gases is the topic we are going to be talking about today, and gas laws. And this particular study will be divided into a series of sections. What is a gas? Very important to understand. The general properties of a gas, the kinetic molecular theory of gases, difference between ideal gases and real gases, parameters to describe gases, and then we discuss all the gas laws. There are about 9 to 10 of them. We're going to talk about every one of them. So let's start with the first biggest question. What is a gas? A gas is one of the major states of matter whose particles are in constant random motion. When you're talking about the major particles of matter, or the major states of matter, I meant to say, the major states of matter include solid, liquid, and gas. There is plasma, but we'll talk about that in a different study. But just have this in mind, that gas is the particular state of matter whose particles are in constant random motion. So they're constantly moving. That's the most important thing to take note of. Now, what are the different properties you would see in a particular substance, and you would assume that this substance is a gas? Number one, they have the weakest intermolecular force of attraction between them. And that's that basically. Because it has the weakest intermolecular force of attraction, that is exactly why gases' motion is constant and random. You get, because nothing is holding them together. The implication, there is something holding them together, but the force is very infinitesimal, very weak. It's not as strong as that of liquid, neither is it as strong as that of solid. So the implication is that gases are allowed to move around however they want. Think about it. Smoke. Can you control the direction of smoke when something is burning? Or for instance, you perceive, or you probably spray your deodorant on one side of the room. Will you tell it, okay, be smelling only in this side, don't go to the other side? Or maybe you have a roommate and you put a deodorant on your own side and be like, okay, all the good smell is on you. That's not how it works, because gases have weak intermolecular forces. They have the right and the ability to move around however they want to. So that's number one. Secondly, is that they do not have definite shape nor volume. Because their forces, or the intermolecular force, is weak, it is what gives it that feature. It now moves around. There's no particular shape it would have. It doesn't take a particular shape because the forces holding them together is not strong or definite. Also, it does not have a particular volume. Now, they are compressible. Amongst all the states of matter, the gases have the highest distance between particles. And the implication is that you can reduce that distance, and that is what compressibility is. In the case of solids, the distance is practically infinitesimal. They vibrate within a very small mean position, which means compressibility is going to be impossible, or if possible, very hard to do with respect to the solids. But for gases, the distance is much, which means we can reduce or shorten that distance. That is what compressibility is all about. Then the fourth property is that they can flow and diffuse fast. Obviously, yes, you pour, as I said, you spray a deodorant on this side, it's already on the other side, very fast. Unlike water, if you pour water on this side, it has to have a slope. If there's no slope, in most cases, it will not flow as fast as. But once it is a gas, once you just put it there, it's going everywhere. You have a balloon, you just pierce the balloon or put a pin through the balloon. Before you know it, everything is everywhere. So that's that basically about gases. They can flow and diffuse fast. Then finally, they have a low density because their particles are well spaced. Talking about density, density is described as the mass to volume ratio. And when you talk about the mass to volume ratio, you are simply looking at density. Now, to understand this, let's just briefly look at our screen a little bit. Take this out and come back to our board. So imagine, for instance, as I said, density is given or expressed as density is equals mass over volume. The implication is that if the volume is increasing, the density will be decreasing. And as we said, if you consider the property we talked about, we said that gases have low density. Now, the space occupied by a substance is what describes its volume. The implication is that gases have the ability to occupy any space they find themselves, which means the space they occupy is quite large. Compared to their mass, the implication is that it will now cause a reduction in density. Now, please, this is what I refer to. What I'm talking about is collective volume and not point volume. The volume of a point mass of gas is practically non-existent. That's why for your ideal gases, they have point masses. But that's something we are going to be discussing ahead. So just note that once you have a gas, it is characterized by these 5 properties. Now, once you are discussing the kinetic theory of gases, the very question that comes to your mind is, how many are they and what do they entail? The kinetic theory of gases more or less describes the relationship between point particles and the kinetic energy they possess. So the emphasis is, how does kinetic energy tend to alter or affect the properties of point particles of gases? That's basically that. So we're looking at these theories. Before we get to discuss them, it's important that you also take note that kinetic theory of gases majorly applies to ideal gas situations or ideal gases. That is to say, if a gas is not ideal or does not exhibit ideality, the implication is that it is likely not going to follow these kinetic theories. So, kinetic molecular theory of gases majorly describes the properties of a supposedly ideal gas, which is more or less theoretical than practical. But let's move ahead. Now, the first theory that is described in kinetics of gases is that gas molecules are in constant random motion. It's very obvious that once it is an ideal gas, it is supposed to constantly be moving. The major reason a gas motion would be constantly in motion is simply because the collision between gases are elastic. So just have that in mind, that anytime a gas, an ideal gas, is colliding, its collision should be perfectly elastic. And a perfectly elastic collision implies that no energy is lost and then the momentum remains the same, which means velocity remains constant. And if your velocity remains constant, it means that you would always keep moving. That's exactly why gases are in constant random motion, because the collision is perfectly elastic. We go to the next property. Combined volume of the gas is negligible. Obviously, if you actually look at the actual points or masses of gases and bring them together compared to the space they occupied, you would find out that the actual volume is quite small. It's negligible. They just have a high distance or large distance between each other, hence giving it the ability to expand and occupy large spaces. The third property is that the particles of gases exert no force on one another. The forces they are talking about here is attractive force or repulsive force, which is something we are going to be discussing. Number 4 is that, as I said earlier, any collision between particles is perfectly elastic. Perfectly elastic collision means that there is no reduction in kinetic energy, neither is there going to be a change in momentum. The implication is that velocity would remain constant. And then finally, average kinetic energy of a molecule is directly proportional to absolute temperature. To the slide. Having discussed the kinetic theory of gases, it is also important that you now take note of the fact that this kinetic theory describes ideal gases, which means if the gas is not ideal, it is likely not going to exhibit these properties. So the question is, what is an ideal gas? So, an ideal gas is a theoretical gas. that obeys all the postulates of the kinetic molecular theory of gases, more like the perfect gas. But then, as I said, it's theoretical, meaning that it's not practical. It doesn't necessarily or really exist in nature. It's just more like an idea of what a perfect gas should be. Now, real gases, which are the ones we have, can actually attain ideality. That is, they can be conditioned in such a way that they begin to exhibit or act like the ideal gases. However, actual ideal gases is just a thing of theory. It doesn't actually exist. Let's move ahead. Now, the properties of such gases that are referred to as ideal include, number one, they are always in constant random motion. You are basically stating the properties of the kinetic molecular theory, because that is what an ideal gas is. It obeys all those theories. Number two, the gas molecules are point-like. Point-like implies that the volume is negligible. That's basically what it means. They do not occupy any volume. Number three is that they experience perfectly elastic collision, which we said before. And this perfectly elastic collision is what leads to the constant random motion, because there is no decrease in the kinetic energy, neither is there going to be a decrease in the momentum or change in the momentum instead. Now, moving ahead, number four, all gases at the same temperature have the same average kinetic energy. So once it's showing a relationship between temperature and kinetic energy, that there's a direct proportionality, that once it is at the same temperature, the kinetic energy will also be the same thing. Same thing. So let's continue. There is no attraction or repulsion between gaseous molecules. So this is basically the postulates of the kinetic molecular theory. You get? So once a particular gas begins to follow all these things exactly as stated, it is said to be ideal. As I said, the ideal gas is more like an idea. It is not a practical gas. That's why it is referred to as a theoretical gas. We'll go to the next one, which is understanding what a real gas is, which is the ones we have here. So, real gases are gases that do not obey all gas laws under standard conditions. So, they do not obey the gas laws under standard conditions. Neither do they follow the postulates of the kinetic theory of gases entirely. Now, one of the major reasons these real gases deviate from the principles of ideality. There are two major things I would like to say about ideality. One of the major factors or major thing in ideality is the fact that there is no intermolecular force of attraction, which means that if a gas is positioned or conditioned such that it begins to have an intermolecular force of attraction, it is deviating from ideality. Take, for instance, let's consider two intermolecular forces. Let's remove this. So if, for instance, we had something like two hydrogen molecules and two ammonia molecules, the force between hydrogen molecules is the London van der Waals force. While the force between ammonia molecules is your hydrogen bond. This London van der Waals force is relatively very weak, while this one is the strongest intermolecular force. Now, ideal gases have no intermolecular force. So the implication is that between these two, the one that would exhibit more ideality is the one that has a weaker or smaller intermolecular force. It looks more like the ideal gas because the force of attraction is practically infinitesimal. An ideal gas should have no force of attraction, neither should it have a force of repulsion. But when you come to ammonia, because it has a strong force of attraction, it is definitely not going to be ideal. So have that in mind, that the stronger the intermolecular force, the more real the gas is, while the weaker the intermolecular force, the more ideal the gas is. Now, the next thing that makes a gas to be non-ideal is when that gas is not energetic. Once a gas is beginning to exhibit non-energetic properties or acting non-energetically, the implication is that it will not be able to collide perfectly in any way. That is to say, the collision can never be perfectly elastic. The reason I'm saying this is because ideal gases have perfectly elastic collision. So when a gas is at a low energy, it will not be excited enough to undergo an almost perfectly elastic collision. So these are the two major things that makes a gas real. Number one is once it begins to show any form of attraction between molecules, reality is dawning on the gas. And secondly is if that gas is not energetic enough, the implication is that it can never have a perfectly elastic collision. Having said this, these are the two major things that induce or causes a gas to begin to act like a real gas instead of an ideal gas. Now, if on the other hand, a particular gas is conditioned such that it has a high temperature, you will notice that increasing the temperature will make that gas to become more energetic. And if it becomes more energetic, the implication is that the collision will now be relatively perfectly elastic, hence giving us a condition related to an ideal gas. So what does that tell us? If I want to make a gas to begin to act as an ideal gas, what do I need to do? I need to raise the temperature to make it very high. The second thing I need to do is that I need to reduce the pressure. When you reduce the pressure of gases in a particular system, you tend to reduce the clustering and make it to be more spread or spaced between each other. And when that happens, you will notice that the interaction between the gases or the forces of interaction will now be negligible. Consider a magnet, for instance. If you bring a magnet together or close to each other, you will notice that the attractive force will be more. But drag those magnets far apart or take them far away from each other, and you will notice that it will seem as if those things cannot have any magnetic force of attraction. Why? The distance between them is now more, hence the effect of the force is reduced. So you have that if you want to make a real gas to begin to act as an ideal gas, two things to do: increase temperature to make it more energetic, and then reduce the pressure so that the distance will be more. The distance between the gases will be high, and once that distance is high, the intermolecular interaction effect would now be highly reduced. On the other hand, if a gas is going to exhibit reality or exhibit real properties, it exhibits these properties at low temperature and high pressure. Low temperature because it would make the gas to be less energetic, and high pressure because it makes the gas compressible, compact. Hence, the effect of the intermolecular forces will now be more noticed. So let's actually try this question to buttress our understanding of the concept of real gases and ideal gases. So let's look at the question. Under high pressure, real gases do not obey the laws because their molecules A have become more energetic, B have become less energetic, C have become smaller in size. Obviously that's so wrong. D decomposes into atoms, and E starts repelling each other. So let's look at that. Under high pressure, once you have high pressure, the implication is that there is an intermolecular force of attraction, and that intermolecular force of attraction does something. It reduces its ideality. One of the ways it's going to use to reduce its ideality is that it is going to prevent it from bouncing off energetically. So the answer is going to be that it becomes less energetic, and that is B. So let's move ahead. There are four major parameters that describe gases. So when you're talking about the property of a gas, you're considering them with respect to these four parameters. The first one is pressure, next is temperature, then you have volume, and then finally number of moles. So let's discuss them in details. What is pressure? Pressure simply describes, or is simply described as, the force per unit area. However, it is important to note that for gases in a container, collision between the gas molecules and the walls of the container is what exerts pressure. So when you are asked a question, and the question is, how do you describe the pressure of gases in a container? Pressure of a gas in a container is exerted as a result of collision between the gaseous molecule and the walls of its container. Not necessarily collision between the gaseous molecules, but that between the gaseous molecules and the wall of the container. That is the one that is prevalent and easily noticed. Now, this particular collision is perfectly elastic for ideal gases. That is to say, there will be no reduction in kinetic energy, and there will also be no change in momentum, which implies that the velocity will remain constant and the gas will keep moving even after collision. The major determinant of pressure of a gas in a container is the frequency of collision. So the implication is that if you change the frequency of collision, you have changed the pressure. If you increase the frequency of collision, you've increased the pressure. If you decrease the frequency of collision, you've decreased the pressure. So that's that basically. So anytime you're talking about the pressure of gases with respect to a container, you find out that that pressure is strictly dependent on how frequent the collision between the gaseous particle and the walls of the container occurs. So let's continue. Pressure can actually be measured in the following units: millimeter mercury, atm, pascal, Newton per meter squared, torr, bar, cm mercury, and the rest of them. However, it is important to note that anytime a particular process is supposed to be accepted universally, that process must be performed under a standard pressure. The pressure in the different parts of the world differs. So when you perform a reaction in Nigeria, the effect or your result will be different from that in the US. So what happens is this: we all need to condition whatever environment we find ourselves such that it is under standard pressure before that particular process is accepted universally. What is the value for this standard pressure? Standard pressure is equivalent to 1 atm. 1 atm is 1 atmospheric pressure, which is equal to 1.013 bar. So if you don't use atm, you could use bar, and the value in bar is going to be 1.013 bar, which is also equal to 760 millimeter mercury, and also is equal to 76 centimeter mercury, which is also equal to 760 torr, equal to 1.01325 times 10 to the power 5 pascal, and finally 1.01325 times 10 to the power 5 Newton per meter squared. So any of these particular relations you think about is supposedly a standard pressure value represented in different units. So if you want to discuss it in atm, you could have that. In bar, you have that. In millimeter mercury, you have that. In centimeter mercury, you have that. In torr, in pascal, these values are values you need to take note of. Now, one of the major reasons I actually want us to take note of these things is because you could be asked a question where the pressure is given in atm, but then you need your answer in millimeter mercury. How do you do the conversion? By using their standard pressure values. Take for instance, let's take this out. Let's take this out and go back to our okay. So in a situation where you are given a question, let's say for instance the question says, what is the pressure of 2 atm in torr? What is the pressure of 2 atm in torr? So how do you convert 2 atm to torr? It's quite simple. First of all, is how many atm makes 1 torr? I mean, how many torrs makes 1 atm? It relates the standard values of the atm and torr. So you have that 1 atm is equivalent to 760 torr. And if that is the case, it means that 2 atm will now be equals x torr. So what do you do in this case? You cross multiply. Therefore, x is going to be equals 2 atm multiplied by 760 torr divided by 1 atm. And if that happens, atm cancels out. 2 times 760, this is going to give us 0215. So that is 1520 torr as the value of 2 atm. So that's that basically. So imagine it was bar and pascal. You simply do 1.013 bar is equals 1.01325 times 10 raised to power 5 pascal. If you do this, you now relate your values and you get your answer. Quite basic. I'm just showing this just in case we need to change our pressure unit. So let's consider this particular question to help us understand the concept of pressure. The question says, an increase in temperature causes an increase in pressure of gases because option A, it decreases the number of collisions between the molecules. Option B, the molecules of gases bombard the walls of the container more frequently. Note that they said increase in the pressure. And remember what we said about pressure, that once you are increasing collision, you are also increasing pressure. Remember, collision between the gas and the walls. Option C, increase in number of collision between molecules. Oh, that's where Jamb comes out and becomes tricky. They gave you increase in collision, but increase in collision for two different things. The particular one that has to do with pressure is collision between the gaseous molecule and the wall of the container. And then finally, it causes the molecules to combine. Now that's the dumbest possible answer there. So which of them should be correct? Obviously is option B. Why? When you increase pressure, or if you notice an increase in pressure, it is as a result of increase in the frequency of collision between the gaseous molecule and the walls of the container, and that is expressed in option B. Having said that, we'll go to the next concept, which is temperature. Now, temperature is generally defined as the degree of hot or cold of a body. However, it can also be described as the measure of average kinetic energy of a particle. Now, mind you, I did not say the measure of average kinetic energy of the whole body, but a particle inside that body. So, if I'm considering the energy of atoms or the energy of molecules, that is basically a measure of thermal energy, which in this case describes the kinetic energy of a particle. So, when you are measuring that thermal energy, what you're actually measuring is temperature. So, just have that in mind, that temperature is a measure of average kinetic energy of a particle, not the whole body. Now, temperature can be measured in degrees Celsius, degree Fahrenheit, or Kelvin. However, the standard unit of measurement of temperature in gases is Kelvin, or absolute temperature. So anytime you are dealing with temperature and it has to do with a gas, if you are given a value in degrees Celsius, you are expected to convert that value in degrees Celsius to Kelvin before you start solving. So just have that in mind. If you have a degree Celsius value, it should be converted to Kelvin before you start solving any question that relates that temperature to a gas. With that said, the relationship between standard having said that, standard temperature of a gas is equal, as just as you have standard pressure, you should also have standard temperature. And the standard temperature of a gas is equal to 0 degrees Celsius or 273 Kelvin. Just take note of those values because they could come in handy when they say at STP. You should just know that ST means standard temperature, which is 273 Kelvin or 0 degrees Celsius, while SP means standard pressure, which is as many as those other values that we have. Okay, so another thing to note is that the temperature at which gases cease to exist, or at which the pressure of a gas becomes zero, is known as absolute zero, and it is equal to 0 Kelvin or minus 273 degrees Celsius. This is what we call the absolute zero. Now, the absolute zero is basically that temperature where there is no gas, because every gas that is existing has either been converted to a liquid or a solid at that particular temperature. So the implication is, if all the gases are converted to liquid or solids, then there's no pressure. That's exactly why the pressure becomes zero, and that is that for that. Moving ahead, if you want to convert a degree Celsius value to Kelvin, all you need to do is add 273 to the degree Celsius value and it becomes Kelvin. If you want to convert a Kelvin value to degree Celsius, all you need to do is minus 273 from the Kelvin and it becomes degree Celsius. Let's basically try out one question to help us understand this. Now, let's remove this and then, see how it goes. So imagine you are given a question and the question says convert 27 degrees Celsius to Kelvin. It's quite simple. Remember that once you are given any question at all with respect to gas laws and it's in degrees Celsius, convert to Kelvin before you start solving. It is very important you do that. So let's get to work. So degrees Celsius to Kelvin, we are told that Kelvin is equals degrees Celsius plus 273, which means that this 27 degrees Celsius plus 273 would automatically make this to become 300 Kelvin. And that's that. Very easy. But if, for instance, I had something like 0 Kelvin and I said that I want to convert it to degrees Celsius, you have that degrees Celsius is going to be equals that Kelvin value minus 273, which leaves me with 0 Kelvin minus 273, and that is going to be equals minus 273 degrees Celsius. So that's that about the conversion. If you are converting degrees Celsius to Kelvin, add 273. If you are converting Kelvin to degrees Celsius, minus 273. Very easy. And that's that basically. Now we'll go into the next parameter that is used to describe gases. And that parameter is what we refer to as volume. Now, volume is described as the space occupied by a particular substance. So, if you are looking at the volume of a substance, it is simply the space occupied by a substance. It can either be measured in cm cube or dm cube. There could be more, like the liter, the centiliter, and the rest of them. However, in our Nigerian curriculum with respect to Jamb, emphasis is on cm cube and dm cube. I'm also going to talk about how to convert these two to each other. But before we talk about that, what is a molar volume of a gas? The molar volume of a gas is simply the volume of 1 mole of that gas at STP. So once you are dealing with a gas, its molar volume is the same for any gas at all. And that volume is equals to 22.4 dm cube per mole, or 22,400 cm cube per mole. Once you are dealing with a gas and it is at STP, the volume of 1 mole of any gas at all is the same thing. And what value do you have for that volume? 22.4 dm cube per mole, or 22,400 cm cube per mole. Having said this, I would like us to take this particular relation before we talk about amount in mole finally. Let's look at this on the screen. The relationship between volume in cm cube and volume in dm cube is given as volume in cm cube is equals volume in dm cube multiplied by 1000. Please take note of this, which means that volume in dm cube will now be volume in cm cube divided by 1000. If I have a question, convert 250 cm cube to dm cube. It's going to be quite simple. Why? When I'm looking for a value in dm cube and I have cm cube, I simply divide that cm cube by 1000, which means that my answer in dm cube is now going to be 0.25 dm cube. Also, imagine I have 2 dm cube and I want to convert it to cm cube. It's going to also be quite simple. Volume in cm cube, when I have dm cube, is going to be volume in dm cube multiplied by 1000. And once I do that, this is going to be 2 times 1000, and then my answer is going to be 2000 cm cube. The extra thing I would like to add is that if you don't see dm cube and you see liter, 1 liter is definitely equivalent to 1 dm cube. So put that down. 1 liter is equals 1 dm cube, which implies that 1000 cm cube would be equals 1 liter, because 1000 cm cube is equals 1 dm cube. A mole of a substance is simply the quantity of that substance that has as much elemental entities as that found in 12 grams of carbon-12 isotope. In some cases, it's MOLS. With this, I presume you've understood some parameters and how to relate those parameters between different values. In this section of the study, we are going to be considering Boyle's law, which is something I'm sure most of you must have come across 1 or 2 times in your secondary school. So what is Boyle's law? Boyle's law states that the volume of a given mass of gas is inversely proportional to its pressure, provided that the temperature remains constant. When you talk about an inverse proportionality, it simply means that as one of these things is going up, the other is going down. So you have that if the volume is increasing, it means that the pressure will be reducing. While on the other hand, when the volume is reducing, the pressure is going to be increasing. Now note that for this particular law to be expressed or taken or to hold sway, you would find out that the temperature must be constant. The implication is that if the temperature is not constant, automatically you cannot talk about Boyle's law, or the volume will not be inversely proportional as it is. So let's move ahead. Mathematically, you express it as V proportional sign to 1 over P. So basically that 1 over P is what indicates inverse proportionality. Then, as we know, to remove the proportionality sign, as math students, we introduce a constant. The constant we are using for this study is K. Now, hence, K will be equals Vp. What this implies is that for a given mass of gas, the product of the volume and pressure would always be the same thing. So V1P1 equals V2P2 equals V3P3, not minding how they change, provided it is the same mass of gas. Automatically, their different volumes multiplied by the different pressures would always give us the same value. Having said this, let's talk about the graphical representation of Boyle's law. Now, Boyle's law is relating pressure and volume, and once you have an inverse proportionality, it is shown by a hyperbole slope. So this particular slope is what indicates the inverse proportionality. However, in this case, you will notice a straight line graph. Straight line graph indicates direct proportionality. But because we have the relation between P and 1 over V, the 1 over V is what is now telling us or showing the inverse proportionality. In this case, the hyperbole curve is showing the inverse proportionality, but in this representation, what shows the inverse proportionality is the 1 over. So just have that in mind, that any of these two representation still talks about Boyle's law. Now note, the slope of the graph of a particular relationship between pressure and volume is known as isotherm. This line of the graph is known as isotherm. You could just think about it. Iso means same, temperature is term. So once you think about a constant temperature, that is what this slope is going to be given. Having said that, we would move on to answering questions. Now, the pressure of 100 cm cube of oxygen at 35 degrees Celsius is 750 millimeter mercury. What will be the volume of the gas if the pressure is reduced to 100 millimeter mercury without changing temperature? So please, I would like you to take your time and take note of these values. Write out different values, because I'll take it out while we are solving. Now, you will notice that the volume changed, the pressure changed, but they told us that the temperature remains constant. And I've said this before. Now, once you want to identify a question dealing with Boyle's law, what you should look out for is the temperature. Once they say temperature is constant, automatically you know it's Boyle's law, and the formula you are going to use to solve this will be V1P1 equals V2P2. So let's get to solve. Bring up my board so that everybody can see what I'm solving. Take this out and then we get to solve. Okay, so solving, I would like to write out the parameters, which is one of the most important things you should do. Write out your parameters. What are your parameters? The initial volume given in this question, which is V1, is equals 100 cm cube, and then the initial pressure is equals 750 millimeter mercury. Now you have that the final pressure is 100 millimeter mercury, and that we were asked to find the volume with this new pressure, which is this basically. Now note, let's look at the slide. Have this in mind, that the initial pressure doesn't necessarily talk about the first value written. The initial pressure is the pressure associated with the first volume, or the initial volume. So now that you have that they mentioned 100 cm cube here of oxygen at 35 degrees Celsius, the pressure associated with it is 750. So this is V1, so this is P1. Because Jamb in some cases can be tricky and then relate the first pressure to the second volume. So you need to be reading your questions well to understand it before you choose your V1 and P1. It's not just the first pressure you see. The initial volume probably could be said to be the first volume. However, the initial pressure is the pressure associated with that particular initial volume. I just wanted to mention this because this is one other way we've noticed Jamb tricks our students and makes them fail. Okay, so let's move ahead to solving this question. Now that we know that temperature is constant, the implication is that we are going to be using our V1 P1 equals V2 P2. And when you use that, what are you going to notice? Putting our values, you have 100 cm cube multiplied by P, which is 750 millimeter mercury, would be equals V2, which we do not know, multiplied by 100 millimeter mercury. Now, if we put all this together, we are going to have that V2 would be equals 100 times 750 divided by 100. Cancels out. Here used to be a cm cube. Here used to be millimeter mercury. So millimeter mercury, but then it will cancel out, and then you have cm cube times 750. So the new volume is going to be 750 cm cube, and that's that basically. Quite easy to understand. Now let's look at our options to see if any of them is there. Okay, and the answer to this question is going to be option D, and that's that basically. So I presume this was easily understood. Let's try one more question, sorry, two more questions, and then we'll call it off by discussing kinetic theory of gases. Okay, so the next question we're going to be discussing, okay, so look at that. They said the ratio of initial to final pressure of a given mass of gas is 1:1.5. So it means that we would assume the initial pressure to be 1 and the final pressure to be 1.5. Just note that. Calculate the final volume. We are asked to find the final volume of the gas if the initial volume, which is V1, was 300 cm cube. Please look at the last part, at the same temperature. So once you notice a constant temperature, automatically you know that that is talking about Boyle's law. constant temperature, same temperature without changing temperature, or they give you 35 degrees Celsius and still say that after the reaction is still 35 degrees Celsius, meaning that it is still the same thing. Whatever way they imply the same temperature, look out for that, and once you see that, automatically you notice that what you are going to use to solve that question is Boyle's law. Okay, so with that said, the initial volume was 300 cm cube. Take note of that. The ratio of initial to final is 1:1.5. So let's go to our board and then get solving. Let's solve. Okay, so let me just take all these things out so we'll have space to solve second question. Now, solving the second question, first of all, is that our initial volume is 300 cm cube. And our initial pressure is 1. Remember, the ratio is 1:1.5. So initial pressure is this one, final pressure is this other one. So if P1 is 1, it means that P2 is going to be 1.5. Having said this, our V2 is what we are looking for. Using our formula, why we are using the formula is because it's constant temperature. V1 P1 equals V2 P2. So with that said, our V1 is giving us 300 cm cube multiplied by our P1, which is 1, will now be equals V2 multiplied by our P2, which is 1.5. Now, putting the units, okay, they didn't give us a unit, but well, it cancels out eventually. So let's go on. So 300 cm cube times 1 is still going to be 300 cm cube divided by 1.5 would give us V2, and when you have that, V2 is going to be giving us, if you do this, this is going to be 200 cm cube. Now, I would like you to notice something, that when you have an increase in pressure, it went from 1 to 1.5, the volume went from 300 to 200, which is confirming what we said about inverse proportionality, which means when you are solving a question and you notice that the volume decreased with a decrease in pressure, it means that you're already solving nonsense. So which means you need to cross-check your work. So have that in mind, that one of the things you could use to check if you are correct is that in inverse proportionality, as one of the parameters is increasing, the other one is going to be decreasing. In this case, pressure was increasing, which means that our volume for sure is definitely going to be less than 300. Okay, so let's look at the options and see what we have there. Okay, so if you look at your options, option A is 120, 200, 450 and 750. Based on what we said, obviously 750 and 450 is definitely not the answer. The answer can either be 200 or 120 cm cube, and from what we solved, our final answer is 200 cm cube. So having discussed that, let us get into the final aspect of this study, and that is kinetic theory explanation of Boyle's law. Now, I would like to, if you look at this diagram, you will notice something, that you have a movable piston, and this piston can move up and down. You would also notice that in this case, when the volume is small, you will notice that the gases can easily hit these walls of the container. Let's look at our board for me to explain this properly. Let's go to our board. Okay, so let's take this slide out and then slide our board in. Okay, so taking everything out, let's continue. Now, if for instance you have two different containers, and note that these containers must be characterized by the ability to have a movable piston. The reason you have that movable piston is just to allow for the change in the volume. It's just to allow for the change in the volume. Okay. Now, for situations where you have a smaller volume, to describe it with the kinetic theory, you will notice that the gases in the smaller volume are more compact. I'm going to use this exact same number: 1 2 3 4 5 6 7 8 9. 1 2 3 4 5 6 7 8 9. So this is A and this is B. So notice something, that when you have a smaller volume, the implication is that the gases will be more compact, and when the gases are more compact, the chances of frequency of collision will increase. Remember, we said something initially, that when you increase the frequency of collision, automatically you are going to be increasing the pressure. So let's take this again. You have a smaller volume, which makes the gases to be more compact, and once they are more compact, collision between the gases and the walls of the container becomes more prevalent or increases, hence it increases the pressure. On the other hand, when you have a larger volume, you will notice that the gases will be less compact, and when they are less compact, automatically collision between these particular particles and the walls of the container will be reduced. On reducing the collision frequency, automatically you are reducing pressure. That's why you notice for a smaller volume, high pressure, small volume, you have high pressure. But in a case where you have a larger volume, what you will notice is that you have low pressure. So that's basically what describes the relationship between pressure and volume using the kinetic theory of gases. Basically, we are going to be looking into Charles' law, so let's get into it. Charles' law states that the volume of a given mass of gas is directly proportional to absolute temperature, or temperature in Kelvin, provided that pressure is constant. The point I'm trying to make is that, first of all, you should be able to note that it is a direct proportionality. That's number one. And then please, you are relating the volume as proportional to what we refer to as absolute temperature, which is the temperature in Kelvin. That is to say, if your values are in degrees Celsius, it is expected that you convert it to Kelvin before you start relating. So I mentioned this in the earlier video, that whenever you are dealing with gases and calculations with respect to temperature of gases, those temperatures should be in Kelvin. So let's take it again. The volume of a given mass of gas is directly proportional to the absolute temperature, or temperature in Kelvin, provided that pressure is constant. So when pressure is constant, as temperature is increasing, automatically the volume should be increasing. Mathematically, it is expressed as V directly proportional to T, as you can see. And then if you introduce your constant to remove the proportionality sign, you have V equals KT. Hence, K would now be equals V over T. And then eventually we'll have, for a particular mass or a given constant mass of gas, the volume over temperature would always remain the same. That is to say, V1 over T1 will be equals V2 over T2. Now, before we solve questions, let's consider the graphical representation. If you consider this particular graph, because it's a direct proportionality for both of the graphs, you have a straight line graph. Now, but the question now is, why is it that this one started from 0 and this one starts behind 0? This is simply because, as I said, the gases, or the volume of gas, is related to absolute temperature, which means we need to start from the origin of absolute temperature, which is 0 Kelvin. That's why from here it started from 0. But in this case, the 0 in this case is in degrees Celsius, and it's not absolute 0. The absolute 0 in degrees Celsius is indicated as minus 273 degrees Celsius. We've actually solved a particular study on this, so please look up the earlier studies on gas laws to get this. Now, having said this, you will notice that both of them are still straight line graphs. And as I mentioned, the slope of the graph in this particular graph law representation, Charles law representation, is referred to as isobar. Why is it referred to as isobar? Because you have that pressure remains constant. Let's move ahead. Kinetic theory explanation of Charles law before we solve questions. Now note, if temperature of a system is increasing, the kinetic energy of the gases will tend to increase, and as they are increasing, it enables them to move more energetically and bombard the container. To maintain constant pressure, a movable piston is used in this description. This movable piston is moved upward as a result of bombarding particles to increase the volume of the container. Let's use our board to help us understand this a little bit. So you have that. If, for instance, let me take away the slide so everybody can see. Okay, slide go away. Okay, I guess we can see the screen now. So now, if for instance you have a particular container, that container, let's say it should have a movable piston. You will notice that if this is at a low temperature, the gases will just be moving less energetically. But once you increase it by introducing heat and raise the temperature, these gases will become so energetic that they begin to heat these particular walls of the container. Now, these other sides are constant, but then this piston is movable. So as the gases are bombarding or hitting this movable piston, it begins to push it up. So notice something, that if this was actually the same container, it pushes this piston up, and you will notice this, that because it is pushing it up, there is an increase in volume. So notice high temperature in this case led to a high volume. So that's basically the kinetic theory explanation of Charles' law. Basically, with this said, we are going to try to solve 1 or 2 questions on this and then continue. So let's try the first question. Now remember that in Charles' law, how you would know that a particular question has to do with Charles' law is once you see constant pressure, or they tell you that the pressure does not change. You have that in mind, that once that is indicated, automatically it's Charles' law. So let's go ahead. Now, a given mass of gas occupies 2 dm cube at 300 Kelvin. So note that the initial volume is 2 dm cube and the initial temperature is 300 Kelvin. At what temperature will its volume be doubled, keeping the pressure constant? So this is a very interesting question. So take note of the values. We are looking for the new temperature when the volume is doubled. Okay, so let's take this out so we can solve. So going back to our board, we are going to have this. Now, you would notice that for this particular situation, you have 2 dm cube as the initial volume, 2 dm cube, and then you have that the initial temperature is 300 Kelvin. Now, because it is already in Kelvin, we do not need to do any conversion. If this was in degrees Celsius, obviously we'll have to add 273 to convert it to Kelvin. But because this is in Kelvin, yes, it's an absolute temperature, so we can solve with that. So they now said that what would be the new temperature when the volume is doubled. So notice that if they say the volume is doubled, it means that it will become 2 times the initial volume. So which means V2 will now be equals 2 multiplied by V1, which is now going to be 2 times 2 dm cube, and that is going to be 4 dm cube. So in this case, we'll have that the new temperature is going to be what? So very simple, V1 divided by T1 is going to be equals V2 divided by T2. And when you have this, basically what happens is we put our values. 2 dm cube divided by 300 Kelvin would be equals V2, which is 4 dm cube, divided by T2, which is what we are looking for. Cross multiplying, you will notice that T2 is going to be 4 dm cube multiplied by 300 Kelvin divided by 2 dm cube. And then if this cancels out and 2 into 4, you have 2 times 300. Our T2 is going to be equal 600 Kelvin. Okay, so let's check our options to see if that is the case. And that is the answer. Basically, that is option D. So you will notice that because we have a direct proportionality between volume and temperature, an increase in the volume would actually be caused by an increase in temperature. So you have that basically. So that's that about that. But then we can actually solve this question without solving that basically with our head. Notice that they said double of the volume. Once volume is doubled for direct proportionality, it means that the temperature would also be doubled. So 300 times 2, and that's your answer. If it was in the case of pressure, if you double a volume, you halve the pressure. But with respect to Charles' law, when you double a particular volume, you also double its temperature, which means if you triple a particular volume, you also triple its temperature. Quite easy, right? Yes. So let's go ahead. Now, the next question we're going to consider is, if 60 cm cube of a gas is heated from 27 degrees Celsius to 50 degrees Celsius, what is the new volume of the gas at constant pressure? So we've already noticed constant pressure, which is trying to tell us that this particular question is going to be a Charles' law question because the pressure is constant. And then secondly, we are relating volume to different temperatures. So once volume and temperature are related at constant pressure, automatically you have that is Charles' law. So let's get to solve. What we're going to do first is to outline our parameters. The initial volume is 60 cm cube, and then they told us that it was heated from an initial temperature of 27 degrees Celsius to 50 degrees Celsius. So I'm going to take this away so we can actually see this on our screen. Okay, so where's our board? Yes, so let's take this out and solve. So we have that the initial volume V1 is equals 60 cm cube. And then we have that it was heated from an initial temperature of 27 degrees Celsius. Now note that if it is given in degrees Celsius, we are supposed to convert to Kelvin before we solve questions with respect to gas law. So we are going to add 273, and once you do that, this is going to be 300 Kelvin. Okay, so we go to the next one. The T2 is 50 degrees Celsius. That is the temperature to which it was heated to. Because it's in degrees Celsius, we also need to add 273. Once you add that, that is going to give us 323 Kelvin. Then we go to the next one, which is V2. V2 is what we're asked to find, the new volume. So let's get to that. Now remember, because the pressure is constant, we are going to be using Charles' law. V1 over T1 equals V2 over T2. If you apply this to this question, you are going to have that V1 is 60 divided by T1, which is 300, which is going to be equals V2, which we do not know, divided by T2, which is 323 Kelvin. Okay, put Kelvin, this is cm cube. Once you cross multiply, V2 is going to be equals 60 cm cube multiplied by 323 Kelvin, all divided by 300 Kelvin. So our answer is going to be equals V2 equals, that should be 64.6 cm cube, and that's that basically. So you notice that when the temperature increased, the volume also increased. Now let's check if that is in the option, and yes, we have that, and that is option C. So basically this is how to solve Charles' law questions. Okay, maybe we'll try just one more question and then we'll call it off at that. A gas sample with an initial volume of 3.25 dm cube is heated and allowed to expand to 9.75 dm cube at constant pressure. So notice that here pressure is constant, and once you see a constant pressure, automatically you should know that that is Charles' law. Now the question now says, what is the ratio of the final absolute temperature to the initial absolute temperature? So let's get to solve this. Because we are sure that this is a Charles' law question, we are going to be using a Charles' law formula. So I'm going to have to take the slide out so we can be able to but then let's take note of our values. Our initial volume is 3.25 and our final volume is 9.75. Take note of that. Okay, so let's take this out and come back to our solving screen. Okay, now because it's Charles' law we are going to be applying, we are going to have V1 over T1 equals V2 over T2, and in this case the initial volume is given as 3.25 dm cube, while the final volume is given as 9.75 dm cube. T1 was not given, T2 was not given, but the question basically is asking us to find the ratio of T2 to T1, which is final to initial, and that's not supposed to be an issue at all. Why? All we need to do is to rearrange this. If you rearrange this particular formula, you are going to have that T2 goes up and V1 comes down, and it becomes T2 over T1 equals V2 over V1. So you have that the ratio of the final to initial temperature is exactly equal to the ratio of the final to the initial volume, which means that the final volume, which is 9.75 dm cube, would be divided by the initial volume, which is 3.25 dm cube. And when that happens, your T2 over T1 is now going to be equals, this is supposed to be 3:1. So let's see if this is in the option. You have that the answer is A, 3:1. I presume you have been able to understand the concepts with respect to Charles' law. In this particular study, we are going to be considering what we refer to as the pressure law. There's usually an argument on who has this law. Gay-Lussac and Amonton both postulated this particular law independently. Amonton postulated first, but he didn't publish it. Gay-Lussac postulated and then published it. However, you might be confused on what they call it. The point is this: whether you see it as Amonton's law or pressure law, they actually imply the same thing. So what is this pressure law we are talking about? Amonton's or pressure law simply states that the pressure of a given mass of gas is directly proportional to the absolute temperature of the gas at constant volume. I take it again. It states that the pressure of a given mass of gas is directly proportional to the absolute temperature of the gas at constant volume. So you have that P is directly proportional to T, but remember that it's absolute temperature, or temperature in Kelvin, not temperature in degrees Celsius. The implication of this statement is that as the temperature is increasing, the pressure is also going to be increasing. Okay. With that said, we move to the next part, and that is the mathematical expression. Now notice that P, removing the proportionality sign, P is equals KT, and then K is equals P over T, which means that P1 over T1 will be equals P2 over T2. The implication of this statement is that the pressure all over the absolute temperature for a given mass of gas at constant volume would always remain the same. So with that said, let's consider the graphical representation of this law. Now, as you can see, once you are dealing with degrees Celsius, it has to start behind 0 degrees and start at absolute 0, which is minus 273 degrees Celsius, or 0 Kelvin. So because it's a direct proportionality in both cases, they are both straight line graphs. And then you will notice that the slope of the graph is known as isochore. Isochore implies that there is a constant volume. So when you are looking at the slope of this graph, or the line of this graph, it is represented or referred to as the isochore. So let's look at this question. Which is the temperature of a given mass of gas initially at 0 degrees Celsius and 9 atm? So the initial temperature is 0 degrees Celsius and the initial pressure is 9 atm. If the pressure is reduced to 3 atm at constant volume. Now, once you notice a relationship between pressure and temperature and the volume remains constant, automatically you should know that that is pressure law, or Hamilton's law. So let's get to it. I would have to take this slide out of the screen so we all can access the writing board. Okay, so with that said, we would solve. Okay, now to solve this question is going to be quite simple. Why? Because we already know what law we are dealing with. Constant volume implies pressure law. So P1 over T1 is equals P2 over T2. Now I would like you to notice something. The initial pressure in this case was given as 9 atm. The initial temperature was given as 0 degrees Celsius. But we don't solve with 0 degrees Celsius. We have to convert to Kelvin. So plus 273, and it is converted to 273 Kelvin. Okay. Then they now said we are looking for the temperature, and then we are given that the pressure was reduced. The new pressure is now 3 atm. So let's get to solve. Quite easy. So putting our parameters into place, this is now going to be P1, which is 9 atm, divided by T1, which is 273 Kelvin, would now be equals P2, which is 3 atm, divided by T2, which we do not know. So cross multiplying, you have that your T2 is now going to be equals 3 atm times 273 divided by 9 atm. Okay, there is Kelvin here. If you remove this and remove this, 3 into here is 1, and this is 3. So you have that 273 divided by 3 would now give us T2 as 91 Kelvin. So that's our answer. Now let's check it out. Let's check it out to see if we are correct, or if our answer is even in the option. So you have that. Yes, and that is option A. So basically, once you are dealing with Hamilton's law or pressure law, you will notice that it simply describes the relationship between pressure and temperature as direct proportionals, provided that volume is constant. In this particular section of the study, we are going to be considering your general gas equation. So it's something that basically is known to most people in secondary school. Now, the general gas equation is basically a combination of Boyle's and Charles' law, showing the relationship between volume, temperature, and pressure. Now, in this particular relationship, neither of the aforementioned variables are constant. So the pressure will change, the volume will change, and the temperature will change. If it was Boyle's law, we would say that in Boyle's law, temperature is constant. In Charles' law, pressure is constant. In Hamilton's or pressure law, you find out that volume is constant. But when you are dealing with general gas equation, how you would know that a question has to do with general gas equation is that nothing is actually constant. Every single thing changes. And once you have that expression, that is what describes the general gas equation. Now, As I said, it is gotten by combining Boyle's law with Charles' law. When you combine this, you have that volume is directly proportional to temperature, which is Charles' law, and inversely proportional to pressure, which is Boyle's law. Hence, after combining, you would have a final expression of V1 P1 all over T1 equals V2 P2 all over T2. So this is what describes the general gas equation. So have this in mind, that when every of the three variables, volume, temperature, and pressure, changes for a particular question, you would know and have that in mind, that that describes what we refer to as the general gas equation. Okay, so let's look at this question. At STP, a mole of chlorine occupies 22.4 dm cube. If the temperature is changed to 35 degrees Celsius and the pressure to 750 millimeter mercury, what is the new volume of the gas? Now, strange things or interesting things that we need to see here is number one, STP. When you hear the term STP, it simply means standard temperature and pressure. And then we've discussed this in our earlier videos. Do watch those videos. That the value of standard temperature is 273 Kelvin, while the value of standard pressure is 1 atm, 760 millimeter mercury, 76 centimeter mercury, 1.013 bar, 760 and the rest of them. So basically, the point is the one we are going to use is dependent on the pressure unit we have in the question. Because the pressure unit we have in the question is in millimeter mercury, the standard pressure value we are going to use would be that in millimeter mercury. And what is that value going to be? 760 millimeter mercury. So let's look at this. The initial temperature is 273. The initial pressure is 760. The final temperature is 35 plus 273. The final pressure is 750. The volume used to be 22.4 and now we're looking for a new volume. What is this thing trying to tell you? Both temperature, pressure, and volume changed. And I told you that once you look at a question where none of these things are constant, automatically you would find out that that particular question is dealing with general gas equation. Okay, so let's actually get to solve this question. So let's take the slide out so we could have space for solving on our solving board. Okay, the slide should be out in 3, 2, 1. Okay, so let's get to solve. Now, to solve this question, as I said, we are going to be applying general gas equation. Why? Because everything changes. So V1 P1 all over T1 is going to be equals V2 P2 all over T2. So let's get to it. The initial volume in this particular question was given as 22.4 dm cube. It was mentioned the initial pressure was standard pressure, and standard pressure in this case is 760 millimeter mercury. Remember, the reason we are using 760 millimeter mercury is because the second pressure that was expressed in the question is also in millimeter mercury. So the standard pressure value you are going to be using has also to be in millimeter mercury. Then we have that the T1 is standard temperature, and the value of standard temperature is 273 Kelvin, as we know. Then we go on. They now say that the new temperature is 35 degrees Celsius. Now, if you have a temperature of 35 degrees Celsius, you do not use that to solve. It must be converted to Kelvin by adding 273. And when you add that, you are going to have 308 Kelvin as the value for your new temperature. Then we have the final pressure was given as 750 millimeter mercury. Now, with this said, we were asked to find the new volume. So let's get to work. Introducing all these things, we are going to have that V1 will now be given as 22.4 dm cube multiplied by the pressure, which is 760 millimeter mercury, all over the temperature, initial temperature. Okay, let's just write this so that would solve with more space. Okay, so solving this, we would have that this is going to be 22.4 dm cube multiplied by 760 millimeter mercury, all divided by 273 Kelvin. Now the final volume we do not know. The final pressure is 760 millimeter 750, not 760, 750 millimeter mercury. And then our final temperature is going to be given as 308 Kelvin. Now, making the new volume to be subject of formula, we'll have that V2 would now be equals 22.4 multiplied by 308 Kelvin multiplied by 760, all divided by 750 times 273. So if you have your calculator, you solve with me. So that's going to be 22.4 divided by 22.4 multiplied by 308 multiplied by 760, and then all divided by bracket 750 multiplied by 273. So when you do that, your answer is going to be equals 25.6 dm cube, and that's that basically. So you will notice that this is basically an increase in volume from 22.4. So that's the answer for this particular one. Let's try one more or two more questions just to buttress our understanding of this concept. Okay, so let's bring up our slide again. Okay, now back to our slides. To what temperature must a gas be raised from 273 in order to double both its volume and its pressure? A very tricky question. To what temperature must a gas be raised from 273 Kelvin in order to double both its volume and its pressure? It's quite simple though. Once you notice that there is a change in both the temperature, the pressure, and the volume, automatically it implies that you are using the general gas equation. So let's use that. I'm going to have to take the slide off so we could use our board. That should come up in 3, 2, 1. Okay, so now let's solve this question. So the implication is that we are looking at a new temperature when both the volume and the temperature, the volume and the pressure was doubled. So we have that the general gas equation V1 P1 all over T1 is equals V2 P2 all over T2. Now note, initial temperature is 273 Kelvin. Let's look at this. The initial volume we do not know, so let's just call it V1. The initial pressure we also do not know, so let's just call it P1. The final volume was said to be double of the initial, as you notice in the question, so that is going to be 2 multiplied by V1. Then you have that the final pressure is also double too, and that is going to be 2 multiplied by P1. Having mentioned this, we have that we are going to be looking for the final temperature, which we do not know. So let's apply all these things to this particular formula and see what happens. So the implication is that we're going to have V1 multiplied by P1 divided by T1, which is 273 Kelvin, is going to be equals V2. V2 is going to be 2V1 multiplied by P2, which is going to be 2P1 divided by the new temperature. If you are actually arranging this, or if you put this and make T2 the subject of formula, T2 is now going to be equals 273 more Kelvin multiplied by 2 times V1 times 2 times P1 divided by V1 P1. So P1 cancels P1, V1 cancels V1. In this case, this is going to be T2 equals 273 multiplied by 2 times 2, and that is going to give us 1092 Kelvin. So basically, you will notice in this case that the temperature was increased to 1092 Kelvin. Having said this, we will be bringing this particular study to an end. Hello guys, welcome to Efiwe, Excellence Without Stress. And in this section of the study, we are going to be considering a very important part, which is Avogadro's laws. So let's get into the study. The first thing we're going to be discussing is understanding what Avogadro's law states. It states that equal volume of gases contain the same number of moles at constant temperature and pressure. So it's important you take note of that. Now, the implication of this statement is that once the volume of gases are equal, the number of moles would exactly be the same thing. So if I have 50 cm cube of nitrogen and it has a particular number of moles, 50 cm cube of oxygen will have that exact same number of moles. Another thing that is implied by this law is that the volume and number of moles are proportional under conditions of constant temperature and pressure. So which means number of moles is directly proportional to volume. Basically, once the temperature and pressure are the same thing, the number of moles should actually increase the volume. You will notice this more when you consider a balloon. As you are blowing in air or maybe the helium into a balloon, you will notice that as more of those particles enter the balloon, it begins to expand or increase the volume of that balloon. That's exactly what Avogadro's law entails. Now we're going to be getting into some questions to help us understand this. The first question we have here, which is a Jamb pass question, is equal volume of all gases at the same temperature and pressure contain the same number of molecules is an expression of what law? Option A, Charles' law, B, Boyle's law, C, Avogadro's law, D, Graham's law, and E, Gay-Lussac's law. Obviously, the answer is C, which is Avogadro's law. Moving on to the next question to help us understand this. 25 cm cube of a gas X contains Z molecules at 15 degrees Celsius and 75 millimeter mercury. How many molecules will 25 cm cube of another gas Y contain at the same temperature and pressure? The answer is going to be the same thing as that of X. Why? Because they have the same volume. 25 cm cube of X and 25 cm cube of Y should have the same number of molecules. And what is the number of molecules according to the question? Z molecules. So notice that they said that the temperature and pressure was constant for this, and that is the condition at which Avogadro's law is established. So we have that the answer is going to be C, which is Z. Why is it C? The two gases have the same volume, which means the number of molecules are supposed to be the same thing. Okay, so we'll consider this question finally on Avogadro's law. Two cylinders A and B each contain 30 cm cube of oxygen and nitrogen respectively at a temperature and pressure. If there are 5 moles of nitrogen, then the mass of oxygen is dash. This particular question has to do with more like a combination of stoichiometry and this Avogadro's law. The first part of the question would help us understand that A and B, if they have the same volume, it means that the number of moles in A and B would be the same thing. So just have that in mind, that for oxygen, if the number of moles of oxygen, as you can see, 5 moles of nitrogen was what was talked about, which means in one of the containers, which is the B container, there are 5 moles of nitrogen. A container is also 30 cm cube because they are equal, which means there would also be 5 moles of oxygen. The question now says, what is the mass of oxygen? So let's get to solve. Let's just go to our screen, our solving board. Take this out in a jiffy. Yeah, so we can now solve basically. So with that said, you will notice that we mentioned something, A and B, 2 containers. These containers have the same volume, and because they have the same volume, it means that here being 30 cm cube would also imply that here is 30 cm cube. If they have the same volume, the number of moles would also be exactly the same thing. So this is nitrogen, this is oxygen. Because nitrogen has 5 moles, the implication is that oxygen will have 5 moles. Now, with that said, we are asked to find the mass, not the number of moles. We have that the number of moles of oxygen is equals 5 moles. But then how do we now find the mass? It's very simple. The relationship between mass and number of moles is expressed as number of moles is equals mass over molar mass, which means that when you are looking for the mass, it's going to be number of moles multiplied by the molar mass. So looking at that, mass will now be equals number of moles for oxygen is 5 moles multiplied by the molar mass of oxygen. The atomic mass of oxygen is 16, and there are 2 oxygen atoms in one molecule, which means 16 times 2. Hence, we are going to have 32 gram per mole here. Now, if this is the case, the mass is now going to be 5 multiplied by 32. 5 multiplied by 32, and that is going to give us 160 gram. So let's look at our options and see if we have that there. So we have that is option D, and that is exactly our answer. So I hope this video has been helpful to your understanding of Avogadro's law and Avogadro's concept. Welcome guys once again. This is Efiwe, Excellence Without Stress. We are going to be considering in this section of the study the ideal gas equation. Now, we'll start by defining what the ideal gas equation entails. It is basically an equation that describes the behavior of a hypothetical ideal gas. Hypothetical because, as I said in the earlier study, no gas is completely ideal. An ideal gas means that it's perfect. However, real gases can be conditioned such that they can begin to exhibit ideal properties. Let's move on. It is derived by combining Boyle's, Charles, and Avogadro's law, which we have discussed in earlier videos. And what is Boyle's law? Volume is inversely proportional to pressure at constant temperature. Charles' law, volume is directly proportional to temperature at constant pressure. Remember that this temperature is the absolute temperature. Avogadro's law, volume is directly proportional to number of moles at constant temperature and pressure. Putting every of these laws together, you would notice that we are going to have an expression V is directly proportional to NT but inversely proportional to P, which if you remove the proportionality sign and introduce a constant R, you are now going to have PV equals nRT. Now, the R in this particular expression, which is the constant, is a constant known as gas constant. The value of this gas constant is dependent on the volume and pressure units. Now we're going to look at them basically, and then I would show us how we are able to derive these things. So let's go to the board so we can be able to understand how they were derived, okay, such that anybody can actually derive them if you don't remember them, but it's important that you just put them to your head. In most cases, you will be given the values directly. You are most likely going to be given the values of these constants in your exam questions. However, in scenarios where or conditions where you are not given those things, the implication is that you might actually be at a crossroad. So it's important to learn how these things are done. Okay, now going back to now let's get to solve this. So as I said, if we are going to be deriving the R value, you simply make it subject of formula, and that's going to be R equals PV all over NT. The R basically is a gas constant that is derived on the basis of your standard values, which means that the pressure is going to be equal standard pressure. Standard pressure, if the particular pressure is in atm, standard pressure value is going to be 1 atm. Then the molar volume is the volume of a mole of a gas at STP, which is going to be equals 22.4 dm cube. In a situation where you are dealing with 1 mole of a gas, N is equals 1, and standard temperature is equals 273 Kelvin. So let's get to solve. It means that when you have your unit as atm, or your pressure as atm and volume in dm cube, the R constant is going to be equals PV, which is 1 atm times 22.4 dm cube divided by 1 mole multiplied by 273 Kelvin. Now when you do this, you are going to have 1 times 22.4, which is going to 22.4 divided by 273 Kelvin, and that is going to give us 0.08025. Now the unit of this is going to be atm dm cube per mole per Kelvin. So just have that in mind, that when your pressure is in atm and your volume is in dm cube, the R value you are supposed to use is supposed to be 0.08025 atm dm cube per mole per Kelvin. So just have that in mind. Now, what if you are not given a particular value in atm and you are given this as your R? You can decide just to convert that particular pressure unit to atm and you have your answer. We've discussed how to do this in our earlier videos, so go and look them up. Also, in the case of dm cube, you could also do the conversion too. Now, having said this, I'll just do one more, which is in a situation or condition where you have your, if for instance you have that your volume was given in dm cube and your pressure was given in Newton per meter squared. Newton per meter squared. What is going to be your value of R? So let's continue. R is going to be PV all over NT. So standard pressure in Newton per meter squared is 1.01325 times 10 raised to the power 5 Newton per meter squared. Then your volume, which is your molar volume in dm cube, is going to be equals 22.4 dm cube. Then you have your N as 1 mole, and then your T as equals 273 Kelvin. So if we put these things here, R is going to be equals PV, which is 1.01325 times 10 raised to the power 5 Newton per meter squared multiplied by 22.4 dm cube divided by 1 mole multiplied by 273 Kelvin. Now, what I'm going to do to be able to cancel out or convert these things properly is that I'm going to change this dm cube to meter cube. One of the reasons I'm doing that is so that our answer would be in joules. So if you change this dm cube to meter cube, what you're going to have is that you're going to have to divide it by 1000 to change it to meter cube, and it becomes 0.0224 meter cube. With this now, we can now get something from here where this particular guy cancels out and you have your meter and the rest of them. So let's continue. So if this cancels out, that means that we're going to have to cancel 2 from here, and this will be raised to power 1. So you have that, such that when the Newton multiplies m, which is force times distance, you are going to have work done, which is joules. So let's continue. I'm just showing us how we were able to derive this. So which implies that R is now going to be equals, multiplying through, this would now be 1.01325 multiplied by 10 raised to the power 5. This all multiplied by 0.0224 divided by 273. If you do that, your value for R would now become 8.313 joule per mole per Kelvin. The next thing I'm going to talk about is ideality of a gas, but I'm not going to discuss it in details for this particular video. We are just dealing with the ideal gas equation. A different section or a different video is going to be discussing compressibility factor and ideality. However, it's important to note these 3 things. If a gas is ideal, the PV over nRT to P graph slope will be equals 1. This PV over nRT is what we call compressibility factor. The compressibility factor, once it is 1, indicates that the gas is ideal, which means that if you check out for the compressibility factor and it is not 1, the gas is not ideal. Number 2 is the slope for the aforementioned graph would be parallel to the p-axis. So if you are looking for an ideal gas expression in this particular relation, the slope is represented by the parallel line to the pressure axis. And you notice that if you look at it, you notice where the ideal gas was labeled as this straight line. These other gases are not ideal. Then finally, at low pressure, gas tends to act more ideal. If you look at this particular expression A and B, in A the pressure is high, and you notice how far they deviated from the ideal property. But in this case, because the pressure is low, notice something like hydrogen is quite close, something like nitrogen is quite close, and the rest of them. So once a gas is situated or is put in a condition of low pressure, the implication is that it begins to act or becomes close to an ideal gas characteristic or feature. We've discussed this in the earlier video, so look it up basically. Now let's move on to answering questions. The question we're going to answer for this particular study is: a sample of a gas exerts a pressure of 8.2 atm when confined in a 2.93 dm cube container at 20 degrees Celsius. The number of moles of gas in the sample is dash. So this is supposed to be a very simple question. So take note of the values. You have 8.2 atm, 2.93 dm cube, and 20 degrees Celsius. The number of moles is what we are looking for. Now, look at the value of R given and compare it to what we discussed before. Liter and dm cube are the same thing, so just have that. And the pressure was given in atm, so we can actually utilize this. Having said this, let's get to work. Now, see what was solved. So if you look at it, you will notice that, as I said, the pressure 8.2 atm, T is equals 20, we had to convert by adding 293. Then we have the volume as 2.93. Now, if you have your R value as 0.08205, you find out that putting this into this particular expression and making n the subject of formula will get us our answer as 0.99 moles. However, you will notice that in the question, it was approximated to 1. So this is going to be our answer. So if you look at this, you will notice that it is 1 mole, and that is option A. Welcome guys to another section of the study of gas laws. In this particular section, we are going to be studying Dalton's law of partial pressure. So let's get into it. The first thing we need to understand is what is Dalton's law of partial pressure. It states that for a mixture of gases that do not chemically combine together, or gases that are not chemically bound together in a container, the total pressure exerted by the mixture is equal to the sum of the individual partial pressures of the constituent gases. So the implication is that if you have multiple gases, 1, 2, and n, all you need to do is to add their individual partial pressures, and then you get the total pressure. For most questions which would utilize this particular formula, you are going to be given the partial pressures of all the gases that are not reacting. And once you are given those partial pressures, if you put everybody together, you will get your total pressure. Now, on the other hand, if for instance you are looking for one of the pressures and you are given the total pressure in a question, all you need to do is a difference of the rest of them from the total pressure, and you have your answer. I presume this is quite simple to understand. The place it becomes tricky for most Jamb questions is in a situation where you are not given your partial pressures, and probably you are only giving your total pressure, but you are asked to find the partial pressure of other gases. Let me explain what I mean. Putting out, let's take this out so that everybody can see the board. Okay, so imagine for instance you have a situation where I tell you that two gases were combined in a container, oxygen and nitrogen, and I told you that the partial pressure of oxygen is 2 atm and that of nitrogen is 1 atm. What is the total pressure in the container? P total is going to be equals P of oxygen plus P of nitrogen, and that is going to give us P total equals 2 atm plus 1 atm equals 3 atm. This is for a condition or situation where the partial pressures we are given. Now, there are questions that you could come across where you would not be given the partial pressure of either of these gases. You would only be given the total pressure and given number of moles, but you're expected to find the partial pressure of one of them. Now let's try one more question on this before we get into that aspect. Imagine I said that in a container containing these two gases, the total pressure in the container is 5 atm. Total pressure in the container is 5 atm. Given that the pressure of oxygen is 1 atm, what is going to be the pressure of nitrogen? So the implication is that P total is going to be nitrogen pressure plus pressure of oxygen, and because we are looking for the pressure of nitrogen, it is now going to be equals P total minus the pressure of oxygen. What is P total according to what I just said? 5 atm. And then what is the pressure of oxygen in this case? 1 atm. Hence the pressure of nitrogen would be 4 atm. But it's possible you will come across a question, and in that question you would be expected to find the partial pressure, but you will not be given the partial pressure of the other gases. That is where mole fraction comes into play. So let's look at this. What do you do in a situation when you are asked to find partial pressure but you are not given the partial pressure of the other gases? It's quite simple. You simply use the principle of mole fraction. Now, as I said, what if in a question you only have the total pressure and the number of moles of gases or mass, or even the volume, but no partial pressures. How do you find this partial pressure of the gas? So you will need to use the mole fraction to find the partial pressure. And the first thing we need to understand is what mole fraction is. Mole fraction is simply a fraction of moles. As it is stated, a fraction of a total number of moles is what is referred to as mole fraction, which implies that if, for instance, you have a multiple or a given number of gases, to find the mole fraction, you simply do the number of moles of that gas you are looking for out of the total number of moles of all the gases in the container. Now you can also do that with respect to volume, and it will give you the same answer. Reason: according to Avogadro's law, equal number of moles or equal volumes contain the same number of moles. So for number of moles and volume, you can do volume of the gas you are asked to find divided by the total volume, and then it will give you your answer. However, you do not apply this principle with respect to mass. That is why I said it is not equal to mass of gas over total mass. So let's take this again. When you are asked to find the mole fraction, what do you simply do? The number of moles of the gas you are asked to find divided by the total number of moles of all the gases inside the container, and that would give you your mole fraction. Now, how do we apply that particular formula to find the partial pressure of the gas? The partial pressure of gas will now be equals mole fraction times total pressure, and that is that basically. Okay, let's solve one or two questions to help us understand this. Now, in this question we have that 0.75 moles of cyclopropane and 0.66 moles of oxygen are mixed in a vessel with a total pressure of 0.7 atm. What is the partial pressure of oxygen in the mixture? So I'd like you to take note of the values: 0.75 mole for cyclopropane and 0.66 mole for oxygen, and then the total pressure is 0.7. We were asked to find the partial pressure of oxygen in the mixture. Based on what we just said, let's take this out. You would find out that if we are to solve this, it's quite simple. We would use the formula that we are given. Once you have a situation where the partial pressure of the other gases is not given, and you are still expected to solve for this, so you will notice that if you have a situation or condition where you are given the number of moles and asked to use the number of moles to find the partial pressure, what you're going to simply do is, using the formula, P of that gas equals number of moles of the gas in question divided by the total number of moles multiplied by the total pressure. So if you do this, we are going to have this. Now, because we are asked to find the partial pressure of oxygen, as we have seen in the question, let's look at the question again. So looking at the question again, you will notice that we were asked to find the partial pressure of oxygen in the mixture, where oxygen has 0.66 mole and cyclopropane has 0.75 mole. The total pressure is 0.7. So let's put this in this formula and get our answer. It's quite simple. So taking this slide away so we would all see what we're doing. So P of oxygen will now be number of moles of oxygen divided by total number of moles. That's NO2 plus N of cyclopropane multiplied by the total pressure. So let's write out our parameters. Our parameters will have that pressure of oxygen we do not know, but we know that the number of moles of oxygen in this question is 0.66 moles. Also, we know that the number of moles of cyclopropane is equals 0.75 moles. And then finally, the total pressure is equals 0.7 atm. So let's apply this and get our answer. So partial pressure of oxygen will now be equals, the number of moles of oxygen here is 0.66 moles divided by the total. That means we are going to add the number of moles of all the gases in the container, which is just oxygen and cyclopropane, 0.75, and we'll multiply that by 0.7. What we're going to have is going to be equals 0.66 divided by 0.66 plus 0.75. 0.75 is equals 1.41, which is going to be multiplied by 0.7. So in that case, we'll have 0.7 times 0.66, all of them divided by 1.41. And if you do this, your answer is going to be equals 0.3 approximately. So let's look at our slide and see if 0.3 is in the option. So yes, that's that basically. Okay, so we have 0.32, just in case for those of you that might 327, which is approximately 0.33. I didn't do it, I didn't check the options. So if you look at the options, basically you will notice that our answer is option D. And why is it option D? Because it's 0.33 approximately. Okay, let's try one more question or two more questions just to buttress this. The partial pressure of oxygen in a sample of air is 452 millimeter mercury, and the total pressure is 780 millimeter mercury. What is the mole fraction of oxygen? Now, once you hear a question that has to do with mole fraction, you have to be given two things. If they don't give you number of moles, they'll give you pressure. So let's get to solve this thing. Because they did not give us number of moles, it means that we expected to use the pressure to solve this. So I'm going to take this out so we can look at our solving screen or solving board. Okay, so let's get there. So having said that, you will notice something, that anytime you are given a question with respect to mole fraction, partial pressure, or you are given number of moles and expected to find partial pressure, the formula to find it is P of that gas equals mole fraction multiplied by total pressure. Now, if you make mole fraction the subject of formula here, you find out that the mole fraction N of G over N of T would be equals P of gas all over P of T. And you find out that you can actually solve that question. We're asked to find the mole fraction. So let's look at the parameters again. What were we given in this question? We were told that the partial pressure of oxygen is 452. And then we are given the total pressure to be 780. So which means if we do 452 over 780, automatically we've gotten the mole fraction. So let's get to solve that. So solving, it will now be mole fraction, which is N of gas over N of T, equals the partial pressure of the gas. The gas we're dealing with is oxygen. That's why we are dealing with that. And that's going to be 452 divided by 780. Remember that it's in millimeter mercury. Divided by 780 millimeter mercury. If you do this, 452 divided by 780 is going to give us 0.579. Now it cancels out. There's no unit for mole fraction. You get. So let's see what happens and check out our options. Okay. So considering the options, you find out that our answer is option B, because that is 0.579. Okay, now having said this, we would go to another part of this study, and that part is what I refer to as your dry gas and wet gas study. Whenever a gas is collected over water, it is a mixture of the dry gas collected and the water vapor. This actually implies that the total pressure becomes a sum of the partial pressure of water vapor, specifically the pressure of the water vapor and the pressure of the dry gas. So if you look at the formula we can generate from this statement, total pressure when a gas is collected over water is equals the pressure of the dry gas plus the vapor pressure, which means that the pressure of the dry gas will be given as total pressure minus vapor pressure. So have this in mind. Anytime you see a question and they say that this gas is collected over water, any pressure they give you there is not a correct pressure yet. For you to get the correct pressure of the gas, you would need to minus or remove the vapor pressure. So just have that in mind. Now, once a gas is collected over water, it carries the pressure of vapor. So which means if you are going to use that gas pressure to solve anything, you will need to first remove the vapor pressure to get the pressure of the dry gas. Okay, so considering this question, the question says, what is the partial pressure of hydrogen gas collected over water at standard atmospheric pressure and 25 degrees Celsius if the saturation vapor pressure of water at that temperature is 23 millimeter mercury? So we take it again. What is the partial pressure of hydrogen gas collected over water at standard atmospheric pressure? So because we saw collected over water, whatever pressure they give us there, would not actually be the pressure of the dry gas, but the pressure of the mixture of both the gas and water. So let's take it again. What is the partial pressure of hydrogen gas collected over water? When it was collected over water, it was collected at atmospheric pressure. The value of standard atmospheric pressure is 1 atm, but because our value is in millimeter mercury, we are going to use the version in millimeter mercury, which is 760 millimeter mercury. Now the question is asking for the partial pressure. We are given the vapor pressure of water, which means this should be very easy to solve. So let's take the slide out and have our board, okay, to solve this question. So to solve it, we are going to use the formula. Once you see collected over water, it means that the pressure of the dry gas, which is the partial pressure of the gas when it is collected over water, will now be the total pressure minus the vapor pressure. Now remember, the pressure at which it was collected is the total pressure, and that total pressure is atmospheric pressure according to this question, which is 760 millimeter mercury. Now the vapor pressure was given, and it's always going to be given at the same temperature, and that is equals 23 millimeter mercury. So how do we solve for this? It's very easy. The pressure of the dry gas will now be equals total pressure 760 millimeter mercury minus the vapor pressure, which is 23 millimeter mercury, and then you are now going to have that the pressure of the dry gas would be equals 737 millimeter mercury. Okay, so let's look at that. Let's check our options once more. So bringing back the slide, you will notice that that is option A, and that is that basically about your pressure collected over water. So this part of the study describes how to get the pressure of dry gas. So note this, that once they tell you that a gas is collected over water, whatever pressure they give you there is the total pressure of both the dry gas and water, which means you need to remove the vapor pressure before you utilize whatever pressure you are given in solving a question. Okay. So let's consider this particular question, which is a combination of multiple laws, also including this particular Dalton's law of partial pressure. Now 50 cm cube of a gas was collected over water at 10 degrees Celsius and 765 millimeter mercury. I told us already that once you see collected over water, any pressure they gave you there is not just the pressure of the dry gas. You need to remove the vapor pressure before you utilize it in solving a question. So they now said calculate the volume of the gas at STP. If the saturated vapor pressure of water at that temperature is 5 millimeter mercury. So let's go to our screen and then get to solve. So take this out. Take note of the values. 50 cm cube of the gas is the initial volume, 10 degrees Celsius is the initial temperature, and then 765 millimeter mercury is the pressure when it is collected over water, which means it still contains vapor pressure. You will need to remove the vapor pressure before you utilize it as a pressure for this calculation. The question now says what is the new volume at STP. So let's get to solve. If we go to our board, you will notice that we would have okay, so let's get to solve. Writing out our parameters first. The initial volume is 50 cm cube. The initial temperature, which is T1, is 10 degrees Celsius. But I've told us that you don't solve with 10 degrees Celsius, you solve in Kelvin, which means we need to add 273. And once we add 273, this becomes 283 Kelvin. Sorry about that. Okay, so this becomes 283 Kelvin. Now the initial pressure they gave us is 765 millimeter mercury, but remember that this is not the pressure of the dry gas. This is the pressure of the dry gas and water vapor. So let's first remove the water vapor pressure. If you look at the question, let me put it up again, you will notice that you were given your water vapor pressure as 5 millimeter mercury, which means we need to minus 5 millimeter mercury from that wet pressure for us to get the actual pressure of the dry gas. Okay, so going back to the board so we can continue. So you have that. This is now going to be so T1, you have that P1 is equals this. So for us to get the actual pressure here, we need to minus the vapor pressure, which is 5 millimeter mercury, and once you minus it, you have 760 millimeter mercury. Now the question says what is the new volume at STP, which is standard pressure. Standard pressure is 760 millimeter mercury millimeter mercury, and then STP, standard temperature, is 273 Kelvin. So if you look at this question, you will notice that our final or actual value of the pressure is 760 initially, and you have that it is still 760 after, which means that pressure is constant. And I've told us that once pressure is constant and volume and temperature is related, automatically we are dealing with Charles' law. So what formula are we going to use for Charles' law? V1 over T1 is equals V2 over T2. In this case, if you introduce your parameters or your values, this is going to be 50 cm cube all over T1, in this case, which is 283 Kelvin, will now be equals V2, which we do not know, divided by the final temperature, which is 273. If you cross multiply, you are supposed to have that V2 will now be equals 50 multiplied by 273 divided by 283. If you do this, your answer is going to be 50 times 273 divided by 283, and you have that your answer is going to be 48.2 cm cube. So let's check if that is in the option. So I'm looking through our options. You have this. Okay, so 48.23 cm cube is option D, and that's the answer. So notice that they gave 48.5, 48.8, and 49.19. Any little mistake you had made would probably have gotten you at the wrong answer, but the correct answer is option D. I presume with this particular study you have been able to understand how Dalton's law applies to nature and how to utilize these different formulas to resolve your question. Welcome guys to Efiwe, Excellence Without Stress, and in this section of our study of gas laws, we are going to be considering Gay-Lussac's law. A very interesting thing about Gay-Lussac's law of combining volume is that it is the only gas law that has to do with a reaction between gases. Every other gas law does not describe a reaction between gases except the Gay-Lussac's law. So let's get to understand this interesting law. What does it state? It states that when gases react, they do so in a volume which is in a ratio to one another and to the product if it is gaseous. I take it again. When gases react, they do so in a volume which is in a ratio to one another and to the product if it is gaseous. So the implication is that let's describe this specifically in our board. But before we go to our board, you notice something, that this ratio is equivalent to the ratio of the number of moles of gases in a balanced equation. So take for instance, you have let's take our slide away so we can see the screen. Okay, so take for instance, and let's say you have a particular reaction. Nitrogen, which is a gas, is combined with hydrogen, which is another gas, to produce ammonia, which is another gas. Okay, so if we are to balance the equation, we are going to have here as 3 and 1 1 1 3 is to 2. So the question now says, or what this law is trying to say, is that anytime gases are combining, each of their volume is combined in a specific ratio, and that ratio is expressed by this number of moles. How many moles of nitrogen do we have here? 1 is 2, 3. Now, because the product is gaseous, that is why we are involving it in this particular expression. If it was not gaseous, we are not going to involve it. So just note that it states that when gases react, they do so in a volume, and those volumes are in a ratio to one another and to the product if that product is also gaseous. So that's why we involved ammonia, because it's gaseous. So that's going to be 1 is to 3 is to 2, which means if I have 50 cm cube of nitrogen, I would have 3 times that 50 cm cube for hydrogen, and then 2 times the 50 cm cube for ammonia. And that's basically how these things work, that anytime gases are reacting, there's a specific ratio for that reaction. If hydrogen, for instance, which is a gas, is reacting with oxygen, which is a gas, to produce water vapor, which is water in gaseous state, and we happen to balance this equation, we'll have that the ratio is 2 is to 1 is to 2, which means if I have 50 cm cube of hydrogen here, I should have 25 cm cube of oxygen, and then 50 cm cube of water produced. If I have 10 cm cube of hydrogen here, I am going to have 5 cm cube of oxygen, because the ratio is 2:1. The basic principle or basic thing we are doing is, if 2 equals 50, therefore 1 will be equals x. Cross multiplying, you find out that x is going to be equals 50 divided by 2, and x is going to be equals 25 cm cube. So basically that's the whole concept behind Gay-Lussac's law. It's just trying to express a ratio of the volumes that are reacting. And I said that one of the easiest way to find out that ratio is by looking at the number of moles in the balanced equation. Once you write them out, you've gotten your ratio. Okay, so we are going to be talking about some other things with respect to this particular law. And okay, so the slide will be on the screen and everybody sees it. The next part, or the next thing that you must take note of, is that the substance whose volume is used to determine the ratio is called the limiting gas. Now you might be given a question where different or variable volumes of gases is given to react, and you will notice that not every given value will be used. Now, to determine the amount that is going to be used, you will need to identify the limiting gas. The limiting gas, or the limited gas, is the gas that is going to be completely used up in the reaction. The second type of gas, based on what we are discussing, is the gas that is in excess. Now, that excess gas is the gas that remains after the process is completed. I'm just going to give us an illustration before we get to solve questions. Now, imagine, for instance, I have hydrogen, which is 2, reacting with oxygen, also a gas, to give water vapor. That's water in gaseous state. Okay, so we've established that the ratio is 2:1:2. Now, imagine you have a question, and in the given volume, we have 40 of hydrogen given and 40 of oxygen given. Whenever they are going to react, you will notice that it is not 40:40 that will react. What is going to react is 40:20. So mind you that the amount of oxygen that is going to react is only 20, which means that there will be a remaining gas. The volume that will not be used is what we call the volume of excess gas. The volume of the reactant that is not used, as I say again, is what we refer to as the volume of excess gas. And the excess gas is that particular gas that will be remaining after the reaction. So you notice that there will be 20 cm cube of oxygen remaining. If you notice, when we are giving 40 in hydrogen, we used all the 40. But giving 40 of oxygen, you are not going to use all of them, because the ratio is 2:1. For every 40 you use of hydrogen, you need 20 of oxygen, meaning that you will have 20 remaining. That 20 that is remaining is what we refer to as the volume of unused gas. Volume of unused gas. So the volume of unused gas is the gas that is remaining, or the volume of the excess gas that is remaining after the reaction is done. So notice that I did not say 40:80. Why? Because I don't have up to 80 here, but I can say 40:20 because I have 20, and then the remaining will be used or taken as the unused gas. Okay, having said this, let's look into some more things about this, and then we start solving questions. Okay, now, having said that, the second point that we are going to talk about is that the volume of residue gas is equals volume of unused gas plus volume of gaseous product. So the implication is that if you are given a question, and in that question you were asked to find the residue gas, first thing you need to do is to find the unused gas. Then you add it to any volume that is found with respect to the gaseous product. I did not say the volume of the products, but the volume of the gaseous product. So if there's any gas on the product side and you are able to note its volume, then you should add it to the unused gas to get what we refer to as the residue gas. The residue gas is what is the total volume of gas that is remaining after you have performed the reaction. And the two gases that are going to be remaining are the ones that you did not use and the ones that you produced. If you put them together, that is what is going to give you your residue gas. Okay, so we're going to try out questions to help us understand this concept more easily. Okay, so let's look at this question. The question says, what volume of hydrogen will be produced if 100 cm cube of ammonia is completely decomposed at constant temperature and pressure? The equation for the reaction is 2 ammonia decomposing to give nitrogen and hydrogen. So the first thing we are going to do is to write down an equation for this reaction. This is a very is an application of Gay-Lussac's law of combining volume, because we are combining different volumes of gases. So let's take this out. Okay, so having said that, the reaction is ammonia decomposition. 2 of ammonia is being decomposed to give 1 nitrogen plus 3 hydrogen gases. So note that all of them are gases, and when all of them are gases, we can actually write out their ratio. 2:1:3. Now let's look at that question again. Looking at the question, so we'll grab exactly what they want or expect from us. We were told that a particular volume of ammonia was decomposing, and that volume is 100 cm cube. Now, after it completely decomposed at constant temperature and pressure, we were told to find the volume of hydrogen that will likely be produced. Okay, so this is supposed to be a simple question. Once you understand it, you will be able to solve it. So let's get to work. Now, if you notice in this question, ammonia is 100 cm cube. If ammonia is 100 and it is 2, nitrogen, which is 1, will now be 50 cm cube, which implies that hydrogen would be 150 cm cube. And that's the answer. Now, but if you want to solve this thing, it's going to be quite basic. If 2 equals 100 cm cube, therefore hydrogen, that is 3, would now be equals x. What do? You cross multiply. So x is now going to be equals 3 times 100 divided by 2, and that is going to be equals 150 cm cube. So that's that. And this was only solved as a result of our understanding of Gay-Lussac's law. Okay, with that said, let's try one more question to be able to understand this. One more question on Gay-Lussac's law, and then we'll call it off at that. 60 cm cube of hydrogen are packed with 20 cm cube of oxygen at 100 degrees Celsius and 1 atm. The total volume of residual gases is dash. So let's take a look at this. Hydrogen is packed, meaning that hydrogen is reacting with oxygen, and we are given volumes, and then we are asked to find the residual gas. The first thing I would like to write out is the formula for residual gas. So taking this out and then coming back to our screen. We'll come back to the question though, but let's get things started. If you are asked to find the residual gas, what is the formula for residual gas? You find out that the residual gas formula is equals the volume of unused gas plus the volume of gaseous product. So let's write the reaction first. Hydrogen is reacting with oxygen, and then it is going to give water vapor first before it's condensed to a liquid. So this is going to be gas, and the rest of them are also gases, which means all of them are involved in this ratio. If this was liquid, that's if this particular if we had a liquid in this case, you will notice that we would not actually involve it in that ratio. If water was written in liquid state, the only ratios we are going to use is 2:1. If you remember what we discussed about Gay-Lussac's law, it says that when gases react, they do so in a particular volume, which is in a simple ratio to one another, and to the product. You only involve the product if it is gaseous, which means if the product is not in gaseous state, you do not involve it. Okay, so having said that, let's continue. Because initially it is produced in gaseous state, that's why we are going to do that. So this is going to be 2:1:2. So let's get to work. The amount of hydrogen that was given according to this question, let's see, is 60 cm cube of hydrogen and 20 cm cube of oxygen. So let's put that down. So given Remember, what you are given in the question is what I call the given volume. It's not the volume that is reacting yet. So the given volume of hydrogen is 60, while that of oxygen is 20. Now, if you look at this thing, you would obviously see that when you are reacting, you would use 60 to react with 30. But because you don't have up to 30 here, you cannot use 60 to determine, which means the limited guy or the limited gas is going to be oxygen. So if we are going to use oxygen to determine, it will mean that if we have 20 here, how many are we going to have here? 40. Since the ratio is 2:1 or 1:2, 20 is to 40. The implication is that the excess gas is going to be hydrogen, and then the volume of the gas that was not used is going to be 60 minus 40, and that is going to be 20. So with that said, you find out that there is no remaining gas here. This is 0. You get. So with that said, the volume of the unused gas is equals 20 cm3. Now, from the reaction, you will find out that 40 of hydrogen is reacting with 20 of oxygen, and that is exactly going to give us 40 of water. So that's 40 cm3 reacting with 20 cm3 to give us 40 cm3. The reason is because the ratio is 2:1:2. So that's going to be 40:20:40. With this particular ratio, we've gotten that the volume of the gaseous product is equals 40 cm3. Now, what is the question? What is the residual gas? We are told that the residual gas or the residue gas is volume of unused gas plus volume of gaseous product. If you add those two things, the unused gas is 20 cm3. Hydrogen is the excess gas. Remember, excess means that it is not completely used. And how many was not used out of it? 20. That's the unused gas. 20 cm3 plus the volume of the gaseous product, which is 40. If you add these two, the residual gas that will be remaining after the reaction is going to be 60 cm3. So let's check our question to see if our answer is in the option. So if you look at this particular question, you will notice that our answer is quite there, and that is option A. So that's your answer, basically 60 cm3. I presume that with this particular study, you have been able to understand the principle of Gay-Lussac's law of combining volume. Thank you for watching. Welcome guys, this is Efiwe, Excellence Without Stress. And in this section of our study of gas laws, we are going to be considering Graham's law of diffusion. I presume you already know what diffusion is, and that is the movement of particles from a region of higher concentration to a region of lower concentration. You would also have noticed that in our earlier studies, we mentioned that gases have the ability to diffuse and flow fast. That is why Graham came up with his theory. Now, what is Graham's law of diffusion? It states that the rate of diffusion of a gas is inversely proportional to the square root of the relative molecular mass of the gas, or the square root of its vapor density. So as you can see on the screen, you have that if this is okay, let's derive the I wrote the final expression, but we can actually derive this thing. So we'll see how we got there. So if we take this out, sorry, I'm trying to set up the board so that everybody can see what's going on. Okay, so if you take this out, yeah, so that's that. Now the law states that the rate of diffusion of a gas R is inversely proportional to the square root of its relative molecular mass. You could also say that the rate is inversely proportional to the square root of vapor density. We'll talk about this later, but let's start with this. Now the implication is that if you introduce your constant, this becomes R equals K all over root RMM. Now with this said, if K is made subject of formula, R, which is the rate, will now be multiplying the relative molecular mass. And when this happens, you will notice that you can decide to write it as R1 root RMM1 will be equals R2 root RMM2. I prefer to write it as R1 over R2 equals root RMM2 all over root RMM1. Whichever way you write it is still going to give you the same expression, but just have that in mind that in my own expression or my own version of writing it, if the rate is on top for the first guy, the relative molecular mass would be down. If the second rate is down, it means that the second relative molecular mass will be up on the other side. That's basically what inverse proportionality means. This over this, like it's inverse. So have that in mind. So with this said, we are going to be talking about the relationship and how this vapor density was gotten. The first thing you need to take note of is that vapor density is equals relative molecular mass divided by 2. And you notice a direct proportionality between them, because as the vapor density is increasing, the relative molecular mass is also increasing, and vice versa. That is exactly why we now said that R1 is equals root RMM. If you put the value of RMM here, RMM will now be equals vapor density times 2. Putting that in this equation, you are going to have vapor density multiplied by 2 all over R2. So this is going to be 2 divided by root RMM1. In this case, we now have vapor density 1 times 2. So cancelling out, the root 2 should be able to cancel root 2. So R1 over R2 would now be giving us root vapor density 2 divided by root vapor density 1. So just note that basically these two expressions would be what we'll be playing around in our study of Graham's law. So I take it again. Graham's law of diffusion states that the rate of diffusion of gases is inversely proportional to the square root of relative molecular mass. Having said this, or to the square root of the vapor density. With this said, we'll talk about one final thing before we discuss questions, basically. Okay? Now, you have situations where you are asked to find the rate of a particular gas, and you are given the volume and the time. Rate is simply described as the amount per time, which means for gases that are usually measured in volume, the rate of the gas would simply be expressed as the volume per unit time. So which means the rate will be given as volume over time. Now, if the volume is constant, the rate is inversely proportional to time. And when the rate is inversely proportional to time, it simply means that whenever a gas has a constant volume, the time would now be directly proportional to the relative molecular mass. It's like, how do I put this? Okay, so let's put this down so we can see or understand our expression. Okay, so you will notice that in our expression of this particular law, R is inversely proportional to the square root of RMM. Also notice that the rate is equals V over time. But when this volume is constant, R is inversely proportional to time. So if R is inversely proportional to the square root of RMM, and this same R is inversely proportional to time, it means that time would now be directly proportional to the square root of RMM. This is basically maths. So once you understand proportionality in maths, this should actually make sense to you. So with this said, if we decide to express this, removing the proportionality sign, we can now write it as T is equals K root RMM. K would now be equals T1 or T all over root RMM. So extending this will now give us T1 over root RMM1 is equals T2 over root RMM2. Now I prefer rearranging this to this instead, where I have T1 over T2 is equals root RMM1 over root RMM2. So why am I having 1 1 and 2 2? They are now directly proportional, so I can put it this way. But if it was inversely proportional, I have T1 on top and the RMM1 below. So just have that in mind. Now, as I said, for you to be able to use this particular expression, something has to be constant, and the thing that must be constant to use this expression is volume. So note, the formula above is only used when the two gases diffusing have the same volume. So if they don't have the same volume, this particular formula cannot be used. The T1 over T2 equals root RMM1 over RMM2, that is the direct proportionality, will not be used once the volume is not the same. Now remember that I did not say rate in relation to square root of relative molecular mass as direct proportions at constant volume. I said time. Rate is not time. Rate is expressed as amount per time. However, when you are now relating time to relative molecular mass at constant volume, there is a direct proportionality. But in the case of rate, it's always an inverse proportionality to the square root of relative molecular mass. So take note of these formulas. I write down the formulas fully so we can see them. The formulas that we must take note of include, number 1, the major formula of Mr. Graham's law, which is R1 over R2 equals relative square root of relative molecular mass 2 all over square root of relative molecular mass 1. Put this in your head. Now, as you are solving more questions in the test bank of the Efiwe app, you will notice that these things tend to stick. The second formula that you must take note of is R1 over R2 is equals square root of vapor density 2 all over square root of vapor density 1. Then, in a situation where the volumes of the two diffusing gases are the same, so where you have same volume, you can now use this expression for time in relation to relative molecular mass. T1 over T2 is equals root RMM1 is now directly proportional. That's why the 1 are on top and 2 are below. So you have that divided by RMM2. This, or you say T1 over T2 equals root vapor density 1 all over root vapor density 2. Okay, now the other thing that I think you also need to note is that vapor density is equals relative molecular mass divided by 2, which means that the relative molecular mass is going to be vapor density times 2. If I tell you that the vapor density of a gas is 12, what's the relative molecular mass? It's going to be equals 12 times 2. Hence, the relative molecular mass would now be 24. So basically that. Now, you also have that when you are asked to find the rate, rate is given as volume over time. So anytime you are given a particular question and you're asked to find the rate, but you are given volume and time, all you need to do to find it is equals this. Which means if I ask you to find the time when I'm giving rate, the time is now going to be equals volume over rate. And you have that. Okay, so let's solve some questions to help us buttress this point and understand the concept. Okay, now the question says the rate of diffusion of a gas Y is twice that of Z. Let's take note of this. The rate of diffusion of a gas Y is twice that of Z. Let me just reduce this so that we can be able to still have the question on the screen. Okay. So let's reduce this so that no, that's too small. Okay, I think it's relatively okay. Okay, so we can see it on the screen. So as I said, the question says the rate of diffusion of Y is 2 times that of Z. So anything that is RY will be 2 of RZ. If the relative molecular mass of Y is 64 and the two gases diffuse under the same condition, what is the relative molecular mass of Z? That is supposed to be something easy to solve. So let's go to our board. So I will be able to solve this question quickly. Now, if you bring up the board, let's take these things away. Now, I'm going to be solving on one side of this particular so that we can all see it. Now, remember that they told us that the rate of Y is equals 2 times the rate of Z. So just have that in my RY is equals 2 times the rate of Z. We don't know what the rate of Z is, so let's call it X. So which means that rate of Y will now be 2X, while rate of Z will be X. They now told us that the RMM of Y is equals 64. The question now says, what is the RMM of Z? Very simple. So let's get to work. If you happen to look at this, you will notice that it's Graham's law of diffusion. So we are going to use his formula. What formula are we going to use? R1 over R2 is equals root RMM2 all over root RMM1. So solving, this is now going to be the rate of y. You know, y is, we call y1 and z2. So the rate of y is 2 times that of z. So we'll have 2x divided by the rate of z, which is x, is going to be equals the relative molecular. Okay, let me just rewrite this whole thing so that it would coincide with our y and z, and will not be confused. So instead of writing r1 over r2, I'm going to write ry over rz so that we would understand this. So ry over rz is equals square root of rmmz all over square root of rmmy. In this condition, or in this situation, we are now going to have, putting our values, our r of y is 2x, as you can see. So we'll have 2x divided by r of z, which is x, equals the relative molecular mass of z is what we are asked to find, and then we are dividing by the square root of the relative molecular mass of y, as we can see. So that is 64. To make this thing easier to solve, just take these two things over to the other side, like square both sides, so that the square root would leave. So squaring both sides, we're going to remove this square root, and that is going to now lead us to have 4x squared divided by x squared will now be equals rmm of z all over 64, because the square root has been taken away. So multiplying through, you are going to find out, okay, first of all is that these guys can go, so that it will be easier to solve. The relative molecular mass of z will now be found to be 4 times 64, and 4 times 64 is basically equals 256. 256. It has no unit because it's a relative value, and that is that basically in solving this question. We're going to try just one more question, and then we will call it off at this point. Okay, so the next question we are going to be considering is, okay, so the question says a given volume of methane diffuses in 20 seconds. A given volume of methane, let me try to expand, let me just expand it for now so that we can see it clearly. I would reduce it when we are solving. Okay, so a given volume of methane diffuses in 20 seconds. How long will it take the same volume? So notice something. Once you see same volume and you are expected to solve with respect to time, what should come to your mind is that our time formula that we derived, which is very simple. And then I would like to say that if you are asked how fast means rate, how long implies time. So don't mix the two. When you're asked how fast, it means what is the rate. But when you're asked how long, it means time. So whenever you're asked time, first check if the volume is the same thing for both of the gases. You have a straightforward way to solve it using that formula, directly proportional to RMM, and you have your answer. Okay, so in this case, we notice that they said same volume. Because they said same volume, the implication is that we can use our T1 over T2 equals root RMM1 over root RMM2. Okay, so let's get to solve this question. First, let me slightly reduce this so that we'll have space on the screen to solve. Okay, okay, I presume we can still see it though. Okay, so let's solve this question. Because the volume is constant, we are going to be using the time expression. We're asked to find the time, so, and the volume is constant, so the time expression is T1 all over T2 is equals root RMM1 all over root RMM2. Please do not misplace these things. If it was rate here, you find out that it will be R1 over R2 equals RMM2 over RMM1, because rate is inversely proportional, but time is directly proportional at constant volume, and we established in this question that the volume was constant. So let's write out our parameters. The time for methane diffusion was given, or is given, as 20 seconds, as we all can see. So you have that methane diffuses in 20 seconds. So time for methane, let's call 1 CH4. Let's just change everything, and then 2 is SO2. So 1 is CH4, so that will not be confused as we are solving. So you have that methane time is equals 20 seconds. Now, the molar mass or the relative molecular mass of methane was given in the question as 16. The next thing we were given in this question is the relative molecular mass of SO2. The relative molecular mass of SO2 is given as 64. And then finally, we were asked to find the time taken for SO2 to diffuse, which we don't know. So let's get to work. The time for CH4 is 20 divided by the time for SO2, which we do not know. That will be equals root. The relative molecular mass of CH4 is 16 divided by the relative molecular mass of SO2, which is 64. If you do this, we are going to have 20 over T SO2. Square root of 16 is 4, square root of 64 is 8. Cross multiplying, you have that TSO2 is going to be equals 20 times 8 divided by 4. So if 4 cancels out and 2 is here, you are going to have 40 seconds as your time. So let's look at our options and notice if it is in the option. And yes, that is option C. Basically, this is how to solve it. The final question I'm going to be solving for today is a question that has to do with finding rate. If you look at this question, you were asked to find time, but in this particular question, you were not given the same volume, which means we cannot use this formula we talked about on the screen. Once you notice that the volume is not the same, you can't say that time is directly proportional. Instead, you use the normal rate formula to solve it. I'll show us how. So let's get to solve the question. The question says, if 30 cm cube of oxygen diffuses through a porous spot in 7 seconds, how long will it take 60 cm cube of chlorine to diffuse through the same pot if the vapor densities of oxygen and chlorine are 16 and 36 respectively? Now, because the volume is not the same for both gases, we are not going to use our initial method of solving it. Yes, when you're asked to find time, you can simply just use the time expression. If you use the time relation formula, which is T1 over T2 equals root RMM1 over RMM2, you get your answer straight off. But because the volume is not the same, we can't use this. So what are we going to use? The normal principle in Graham's law. So let's take this out first to be able to solve this. So let's take this out. And then, now, the Graham's law expression we are going to use is basically R1 over R2 is equals root. In this case, we are given vapor density. So vapor density 2 all over root vapor density 1. Now let's look at the question. If you look at the question, you will notice that the gases involved here are oxygen and chlorine. Let's write out the parameters. They gave us 50 cm cube of oxygen and they said that it diffuses in 7 seconds. So let's put that down. We have that the volume of oxygen is how many? That should be 30 cm cube of oxygen, I meant to say. So the volume of oxygen is 30 cm cube. And the time it takes for oxygen to diffuse is 7 seconds. Now, if we are going to find the rate for oxygen, remember I said that rate is volume over time, which means this is going to be 30 divided by 7. And 30 divided by 7 is going to give us 4.2 something. So 30 divided by 7 is going to give us 4.28. So we have that the rate for oxygen would be 4.28 cm cube per second. So 4.28 cm cube per second. Now we were asked to find the time for the other gas, which is chlorine. And if you are going to find the time, you need to find the rate first. So let's resolve that before we continue. Now, the vapor density of chlorine was given as 36, while the vapor density of oxygen was given as 16. So if we put these things in our values, we're definitely getting our answer. So modifying this formula to suit what we want, we are going to remove 1 and 2 and replace them with the names of the gases involved, so that it will become easier to understand. So R the first R is for oxygen, so R of oxygen, rate of oxygen divided by the rate of chlorine. We'll now invert it because it's inverse. We'll now have chlorine on the top and oxygen below because we are dealing with rate. Now, why we are using this formula is because the volume is not the same thing. If it was the same thing and we are looking for time, then we would use the time direct relation. So let's get to solve. The rate of oxygen we got is 4.28. So 4.28 cm cube per second divided by the rate of chlorine, which we do not know, equals square root of the vapor density of chlorine, which we got as 36, then square root, according to the question, of oxygen is 16. If we are to do this, this will be 4.28 divided by the rate of Cl2 equals square root of 36 is 6, square root of 16 is 4. So cross multiplying, the rate of Cl2 is now going to be 4 times 4.28 divided by 6. If you do that, you are going to have 4 times 4.28 divided by 6. Your answer is going to be equals rate of Cl2 is equals 2.85. Now remember that if you look at the question did not say find the rate. It says find the time it would take for 60 cm cube of chlorine to diffuse. Now let's go back to our formula. You remember something in what we discussed earlier. Rate is equals volume over time, which means when you are now looking for time and you have volume and rate, what are you going to do? You will now have that the time is going to be volume divided by the rate. So looking at this, you have that the volume of chlorine involved in this question is 60 divided by the rate we got from what we solved as 2.85. So if you do that, you find out that 60 divided by 2.85 would now have that the time for chlorine to diffuse would be equivalent to 21 seconds. So let's check our options and see if it is there. So as you can see, the answer is option C. Solve more questions with respect to this on Efiwe app. And as you solve these questions, you get to understand this concept the more. Thank you very much for joining me on our journey to understand gas laws.